Right. Assalamualaikum warahmatullahi wabarakatuh. So today I'm going to explain and discuss about the Stokes and Green theorem, which is under the subtopic of surface integration, basically, and also align integration, which is an applied mechanism for more practical solution, especially for the case of applied cases. So before we start together, we recite dua. Bismillahirrahmanirrahim. اللهم افتح علينا حكمتك وانشر علينا من خزائن رحمتك يا ارحم الراحمين رب اشرح لنا صدورنا ويسر لنا امورنا واحلل عقدة من السنتنا يفقهوا اقوالنا رب زدنا علما نافعا وارزقنا فهما نافعا بسم الله توكلنا على الله لا حول ولا قوة الا بالله العلي العظيم العالمين. Right, I try to compress everything, especially for the basic or the fundamental understanding, and we look into the cases, the question, the example, so then you can prepare for your final exam, especially for this topic, which is quite what I call it, applied to the real situation. But again, I try to explain everything, especially on the derivation part. Okay, so for the first step is the Green theorem, which is Green theorem is related to the line integration theorem. Line integration theorem, which is need to integrate the line within the specific region. Okay, before that, so let's start with the understanding of the vector field, which is we already learned in vector field of the squared one for the real in two-dimensional, which is normally we said we're going to understand that in in real Cartesian coordinate of x and y. So if we have a line, basically we refer to the plane, the planar, the plane itself contains of two axes, right? So for example, you have a plane, so you have x and y, so it should be y and x. So this is normally a line within the plane of xy plane. But for r cube or in three-dimensional vector field, so you have, for instance, z direction, x and y. So if your vector field within this domain, for example, so it contains this domain, so it contains of three component of theta, phi, and z value. So this is a three-dimensional. So although the curl is only defined for a vector field in R3, so in three-dimensional, so you have the curl, you know, I mean, as I said previously, for example, you know, a toroidal or what you call it, some like a wind turbine, the wind turn around. We call it, they call it as a toroidal wind, for example. So the wind itself have a vector field, and each vector field contains three-dimensional three-dimensional position. So you have a vector field in three-dimensional. So then from the curl, you know how much or how much the curlity or the value of curl itself dia macam mana dia berpusar. So we used to define the natural important operation on the vector field in R squared. So the curl in R3, and we can use it to define the natural operation on the vector field in R squared. First, given a vector field of W on R squared, and then we can easily create a vector field in R3. We will abuse the notation this to call this new vector field W. We can compute its curl. I mean, even though we say it is in R3, but again, if you look at this position, this vector field, another dimension of vector field, in order to derive a new thing, we just state it as 0, which is more or less, it's only rely on the planar of XY plane. Okay, so to compute the curl of in 3D vector field, but then it's only contain is hold a value of 0 on the z-axis, so you just have a curl t. So the curl formula, as we learned previously, is just a straightforward do a curl to understand or to derive it. So this is the way how to derive, and then you get it. If you notice here, it's only involved in two plane of x and y, even though it is a curl of a vector field in 3-dimensional structure. So this is kind of the way how to derive, right? So if W is a vector field in in R squared, which is R squared real space, then the result of the nabla, the divergence of across with vector W is in a function of R squared. This function acts much like a derivative of W. Even though we first defined it in 3-dimensional space, but then because of the curl, because of the value of the z component is equals to 0, so then right now we just play around. Even though we find the curlity, this is the curlity of the vector field of W, it's only give us within the dimension of W, within the dimension of two planar. I mean a planar of XY. I mean two real space, 2 dimensional, 2 Cartesian of real space, which is X and Y. So this is the trick. So this is the trick on working on the green function. So now we ask what happened when we integrate the result of the such derivative. So that is, if Q is some domain in R squared, we can say that the integration within the domain of Q for the vector field of curlity of W will give us definitely this one, which is this is the curl derived here, and over 2 domain of X and Y. So for simplicity, we assume that there is a domain integration. So then this is a rectangular. In this section, we explore more general domains to understand. So then we try to make it reality. So we can make it. We try to make the explanation into real type of understanding to make it rather than the philosophical, the things that I said just now is very abstract. I mean, so lot of us, lot of student, it's difficult to understand this theoretical part. To understand what is going on in here, we will have to go all the way back to the definition of multiple integral. So Q is some domain in R squared, which is only involved in x and y. So let's see our y and x. So Q is a domain right here. Q is a domain within the plane of xy. Okay, first choose a lattice evenly spaced. So let's say if we say evenly spaced, meaning that to make it understand easier to visualize the structure. So let's say it's become a square part because it is even for each part. So from I to j, so x from the 1 until what numbers. So we can have a point, but it should be evenly spaced. So just like our graph paper, right? So first, the surface can be said as smooth as possible. Smooth as possible because we're going to have a plane, a real plane space. And all of these are will be explained in the structure in the visual part. So for each compute, so then for each point we compute the changes of the previous point. Let's say we have x2 minus x1 will give you the delta of x, which is value of space. For example, we have 3 and 4. So this is your delta x. So your parameter of space is now equals to 1, right? So this is defined. So then next, what multiply of each component. So what did you get of each component and multiply? So you get value of distance, spacing, area of space. So for example, you have x and y evenly spaced. So this is 3, this is 3. So you get, if you multiply 3 by 3, you get 6. 6 is 9. 9 is an area under within the domain of 3, 3. Take a limit and approaching 0. So this is all the step. So it jumps into this one. So this is things that to explain what is the green theorem. So you have and finally we have the summation of everything. For example, we have to understand this one is quite challenging because there's a lot of parameter here, but it is this one is a very simple example. It starts from 0 to 0, until mn. So 0 until m, and y naught until ym. So this is your area of Q, right? Note that each term in the final expression is sum involving the values of f or g at point side of Q. For example, the first sum, we see the expression of g. First sum, the total. The number of n is represent constant numbers, the largest index of the x value. So how many x you want? I mean, it is in practical you have a value, right? So n is a algebraic constant. You didn't know until you do your mathematical problem. So from x0 until n. So summation, which is you add up everything at point, at point from start until whatever number, until hence the point of the form xn until yj must lie in R, the right side of Q. So until, so the point form of xn, so this here, until yj. So what is j? J is definitely depends on the parameter until m. So j from 0 until m, so meaning that every single point you count. So this is a summation of the point. So this is derivative, everything is written here until everything here multiply with x, because this is on x component. So actually for each y also have, so this one multiply for the y component also, you must take it for t part and so on, L, B. So so each of the part prepared. Consider this next step, we take a limit. So this is the limit, so until the derivation of the green theorem of each. So this is the total of integral. So before that, we look one by one. For this integral, the same integral of w over r with the orientation indicate 11(1). So this is the figure. To see this, we parameterize r by psi I from n xn until y. Which is a domain, as I said, from 0 till m. If we parameterize d psi over dy from a vector field of x, y1, which is in upper direction, so this is parameterization of the direction, as we discussed in the case of water flow, the case of the leaf in the river, previous case, which is in introduction of parameterization in line integral. So the parametric give you the direction of the total vector, or the real vector field, something like that. I can say that one. So so if we integrate over the domain R from y0 until ym for the vector w, which is parameterized by psi, vector w which is parameterized by psi within a specific domain. So we have what was supposed to do. So this is y in the function of psi y, right, dot dy. So this is the formula of line integral, as I teach previously. So you get definitely this one. So g is a function. So this is going back to the formula of g, going back into that one. So this is the way to derive it. So what does it mean? So actually the three terms in the sum from the step 4 give a similar integral over this remaining side of Q. So now we are ready to the conclusion, which is within the domain parameterized by R, within the domain parameterized by L, T, and B, we taken all together as a boundary. So the usual notation for this, they call it, they use as, it is not a nabla, it's not a partial, this it is a domain notation for boundary of Q. So then the way to write as a Green theorem is, if we have a double integral of domain Q, which is written as domain boundary Q, for the curl dt of W, or for a domain within the W, as we do it previously, within here within a vector field that's actually in R cube, but then because of the case that the Z dimension equals to 0, it means that we are going to have a planar. So for this case, if we derive it for the curl, we try to find the curl. So the curl becomes like this, is only involved in 2 dimensions. So that is the sign of this case can be used, can be solved. The integration for this case can be solved using a Green theorem. So what is the Green theorem? It's all about the integration within the boundary that lies within the plane of planar of x and y. This is for the case of xy. You might have other notation as well, k and w, whatever it is. So this is Green theorem. So what kind of the problem that involved? It's really simple one. Okay, first we know. Okay, let's see. We have Q. Q is a rectangular of xy. Alright, so you have from domain x 0 until 1, and then from 0 until y equals 1 as well. So the question asks you to evaluate the integral of this vector over the boundary of Q. So this is our boundary, right? So we didn't have any, we cannot draw, we didn't know how the vector of this one looks like. So let's say, I just said let's say, and we didn't know how does it look like. Let's say it's going to be like that, let's say, because we have a squared for both one and one is negative, whatever. So the question asks you to find what will be, let's say, I'm sorry to say, because I didn't know how the vectors look like, right? So it is quite complicated vector. So unless we can draw it, vector field, this kind of vector field in our Python programming, so we know how the vector field looks like. So the question asks you to draw, to calculate what will be the area, which is a green, which is an integral, right? So over the domain, so you have, the domain of Q is given for each part of 1 to 1. So then we have our W, right? So W, and then we're going to parameterize using a specific domain of ds within the boundary of Q. So what we do first, we find the cross product or the curl, and then so we find that one first. So from the formula we know that we get that this one directly for the curl, since the curlity is involved in 2 dimension, so straightforward, you can put this as G, and straightforward this one for F, the FG, this one, and then G, this one. So for the first part, we have G over X. So we have G over partial derivative of X, and then minus F over partial derivative of Y. And then you do straightforward straight away integration one by one, solve it for X and also for Y. So that's all. So you get the value of 2, even though we didn't know how the vector looks like and within this domain. This is the same case. For example, you have a water flow. Imagine everything is in 3D, in 2-dimensional. So within the specific domain of Q, boundary of Q, so we are going to find what will be the area covered, for example. What will be the integration, because we have a lot of line, right? So we didn't know. So let's say you're going to find so then you get the value straightforward by using the Green theorem. Okay, that is for Green theorem. So now I'm going to this is another example. Yeah, we are calculating the area bounded magnetic field line. So you know, when tip field line is not just straightforward line, right? So you have a slightly inclined and straightforward and so on, but you have a boundary within it. You have 1, 5, 4, 5, 4, 1, and 1, 1. So this is your Q. This should be your boundary of Q. So straightforward using the integral boundary, so it oriented in clockwise, so everything in clockwise. Yeah, no, this is counterclockwise. Oh, sorry, I misspelled. Counter, yeah. Definitely. So you just follow the same step given by Green theorem. So this is one of the example. I just want to show you the example, so you might look into this one. So this is one of the case. That's good. Okay, next is Stokes theorem. Yeah, Stokes theorem is about the 3-dimension. As we look at Green theorem, so you as we discussed previously on the Green theorem, so you know it is only involved in G and F for domain involved, right? Because for calculation it's only involved that one. But what happen if you have in real space of 3D? For the Green theorem is a special case of a Z, the last component equals to 0, right? So this is 1 is not equals to 0. I'm going to stop here. I'm going to make the second video of the Stokes theorem. Okay, stay tuned, and we will see. I will continue after this.